Okay, I have started the recording, so I hope you are still able to hear me.
Yeah. Am I
So,
audible also?
yeah.
Oh, fine.
Okay. Right. So, welcome to week 10, optimization from fundamentals. So, just a quick word on what I had said last time. So, I had asked to prove f of x equals to max is convex. This max function is convex if all the fi's are convex. So were you able to do this?
No, I could get the intuitive picture by drawing planes, but I could not formalize my argument. That was I was stuck at.
Okay, so I'll just give maybe two hints, two ways of doing it. So one is for that again you have to show something. So method one. Okay, let me start with a simpler one, which is just applying first principles. Okay. So what will this be? Okay, so just a sanity check, but why will proving this statement about max of is solve what we had done last week? So if you remember last week, we had a bunch of linear functions over which we were taking supremum or infimum, right?
Yeah.
Okay, so is it clear why proving this
Yeah,
statement? Yeah.
it's clear because for each value of x we have a separate linear function, right?
Okay.
And so we want the pointwise infimum of them, right? So that's why
Yeah, but so we can use
doing.
it because linear functions are both convex and concave, right?
Yeah.
Okay, so that's what I was asking. So here, uh, so remember that each of these f1, f2 up to fn they are all convex, and I've given this. Okay, so I'm just applying the convexity definition. Is it fine so far?
Yeah, it's fine.
Okay. So what can we do now? So in every each one of these terms we have two subterms. So what you could do is, so is this fine?
Yeah, I am having a little bit trouble rationalizing this step. So Yeah, so it's a pair, it's a sum of two functions, and you are taking the max of them.
Yeah,
It's
so maybe what I'll
really
do is I'll write it like this. Uh, Lambda x1 plus 1 minus lambda y1. We'll just take two terms and we'll take a very simple linear function. So I am adding these things and then taking maximum. So what I am saying is I am a plus b. Here the candidates, so I had possibilities of a1. Yeah, let me. So if I want to do this maximization, can I say something about this?
yeah, you can maximum of A. So there are two candidate values. So you could do it pointwise, means you can do it as
So there are
uh,
four combinations, right? A1 plus
yeah, four
b1,
combinations.
a1 plus b2, a2 plus b1, a2 plus b2. Okay.
And now you can compare each of them, and means
Okay.
means
So
I don't know whether the ordering is such that A1 precedes A2 or something
no,
like
no.
that.
I
I
mean
don't know.
just something. I mean, so one of the a1. So okay. So for just for concreteness, let's say a2 greater than a1 and b1 greater than b2. Let's say just for this case.
Yeah.
So how
As
can you maximize
as
this summation?
yeah. So you take the highest value of A and you take the highest value of B.
Uh,
Means A2 plus B1.
okay. So you looked at okay. So which case is this? Did we separate out the terms and then took max for each of them, or did you look at the sum and you look at the uh, resulting maximum sum?
No, here for this case I looked at the individual terms and tried to
Yes, yeah.
maximize
So
them.
here I just did this, right?
Mm.
Otherwise, if I wanted to just look at this, let's say
Mm.
forget this, I have four possibilities. I just exhaustively search over them, right?
Yeah.
But one question here. So in this case, I have not said whether these ava sorry this uh, okay, yeah, I have not said in this case whether these a1 a2 b1 b2 are strictly non-negative. Let's say I haven't said that. So will
Yeah.
that cause a problem if let's say some of them are
Uh,
negative values? I mean, let's say zero point 0.5 minus zero point 0.2. I don't know. I'm not sure if this example will work, but let's see. Minus 0.8 minus 2. So let's say if these are the values in that. Let's see if this example works or not. So
so
you
if
you got the
we
question right.
yeah, I got the question. Yeah, that was my doubt in the previous class also. I was not sure about this step.
Okay. So where
Yeah,
where
so
can the thing go wrong?
yeah, when one basically it intuitively looks if one term interferes with the other, then there could be some problems while doing the operation. Uh, means suppose in this case, suppose for the we just go by the logic. We take A2 and B1 as the maximum sum. So in that case, it turns out to be zero point 0.5 minus zero point 0.8. So it comes out to be minus zero point 0.3, right? And if
See,
we do it term wise,
see,
then
I will
yeah,
write it like this.
yeah,
Let's say a plus b, and so okay, I'll just write from here this part. So you know that, or maybe let me rewrite it like this: a belongs to a, and b belongs to b. Okay.
yeah,
So a is less than equal to max. Uh, Let me just call it a star. where A star equals to max A prime right. Similarly B.
A star is equal to maximum of A prime. Okay, okay, fine.
So this is just by definition, right?
Yeah, it's just by definition.
So if I write A, so okay, so if I know this for a fact, this is true, right? By definition. I mean, I have a bunch of elements. I took the maximum and A less than equal to this element, and
Yeah,
similarly B. So then in that case, can I not write the sum as less than equal to sum of the maximum? Like by definition. So if this is true, then A plus B less than equal to A star plus B, and B is less than equal to B star, so that is A star plus B star.
less than equal to A star. Okay. Yeah,
There is no
this.
no
Yeah,
problem here, right?
yeah. This looks okay. Yeah.
So okay, the problem. So let me again. So which one would we use? So we have on the left hand side this, which is what we really are trying to do, and we have this thing here. So do you agree that this holds trivially true?
Yeah, this I agree. Yeah, completely.
Just by definition, right?
Yeah.
Can we say anything about equality? So let's just take this example. I don't know if this will, maybe we'll have to massage the terms of it, but let's see. So in this case, what is our A star? 0.5.
Yeah.
And what is B star? Minus 0.8. Okay.
This. Okay. Yeah.
And okay, so RHS is what? Minus 0.3.
Minus 0.3. Yeah.
Okay, what about LHS? So
LHS
we'll have
we have
to take all combinations, right?
Yes, all combinations. Yeah.
So we have max over. So max over, let's say if this is the A2 plus B1 is some combination, so minus 0.3. Then what other combination will be there? 0.5 and minus 2, let's
minus 2, minus 1.5.
And similarly this minus 2.2 with minus 0.8 and minus 2, right? So minus 1 and minus 2.2.
Yeah, minus 1 and minus 2.
Minus 1 and minus 2.2.
Okay. Oh, so the max is minus 0.3. Yeah.
Okay, unfortunately they are equal here. Okay. So if I put 0.4, let's see. If I put 0.4, then what happens? So this becomes 0.4 A star. Let me also change this to minus 1.5. Hopefully this works. Okay, so A star is 0.4 and B star is minus 0.8. Okay.
Yeah.
Okay, what about, so RHS is what exactly? Minus.
So it will be minus 0.4. Yeah.
Right? Okay. How about? Yeah. What about LHS?
This will be first term will be first term will be minus 0.4.
Right. So minus 0.4, and this with this will give me minus 1.1.
Minus 1.1. Yeah.
Okay, this won't work, I think. Okay, let's see. Anyway, let's just see. I just want to make a point, and if you can't, I'll just quickly move on. You can just cook up an example. You just have to adjust the
Yeah, I got
numerical
the point.
values.
Yeah.
Okay, similarly with minus point 2 and
Okay.
minus
This
point
will,
5. So yeah, this
yeah, this,
unfortunately again doesn't work out.
yeah, this also wasn't hello,
Yeah.
hello,
Yeah. Can you hear me?
hello,
Yeah, I think you might have to
hello,
join again, but
hello,
I'm able to hear you.
hello. Just a minute, just a minute. Hello.
Yeah, I can hear you.
Suddenly the Siri came up and it was interfering in the microphone. That's why.
Oh, okay. Okay. Is it fine?
Yeah, it's okay now. It's seemingly it's okay. Yeah.
Uh, right. So, just wondering what values will work here. think,
No, I was thinking that somehow when we
I
add
mean,
this,
here,
a lesser value a lesser value will come than the pointwise minimum infimum of them. That was my point.
sorry.
I was just wondering if somehow by adding we can decrease the sum further than what we can get by minimizing each one of the terms individually.
Sorry, can you repeat that again? I'm not able to hear.
Yeah. Hello, am I audible?
Yeah, yeah.
Yeah. So I was just wondering if somehow by adding the terms we get a term that is lesser than the minimum of the individual terms.
By adding the terms, yeah. So that's what I want to do actually. Yeah. Um. Yeah, that's exactly what I'm trying to do. So the point that I'm trying to make is the max function is not linear in general.
Uh, Linear means the linear ordering, right?
Linear operation. So if I have a max here,
Okay.
so max of functional plus function, that doesn't mean that it's equal to max of f functional plus max of function. And
Right.
that, as you would expect, comes because of these negative values. So like you
Yes.
were saying, so the max value that I can take here, so I just have to, sorry, something happened. Yeah, the max value, I just need to arrange these values such that I get a strictly smaller max of sum than the sum of the max values. So I
Yes.
mean, just try this out. I don't know, I'm making some silly mistake maybe, but that's the
Yeah.
point I wanted to make. So in
Yes.
general, I
Yes.
all I can say is this,
I got it. I got it. Yeah.
wherein I will remove the equal to sign. So all I have is this. So I have just used that information here. That's all.
Okay. Got it. Got it now. Yeah.
Okay, so what I meant was this. Uh, yeah, so you have a bunch of terms that are being summed, and then you're taking max over that. I'm just saying
Hmm.
in each of these summations, you just so think of this as max of a1 plus b1, a2
Yeah.
plus b2, and so
Got
on.
it. Got it.
So I'm just doing that.
Yeah. So you apply the same thing coordinate wise, right?
Yeah, I mean not a coordinate, but yeah, for each index for each of these
Yeah,
functions
it's
as such.
ordered thing. So yeah. Okay.
Yeah, it's for that pair. I mean, there's no order as such, but it's just the tuple,
Tuple. Yeah. Sorry. Yeah.
right?
Got it. Got it.
So,
Yeah. Got it.
so, so this is lambda times max of f1x fnx plus 1 minus lambda max 1y fny. So let me erase this. So yeah, just try this out. Sorry about this. I think this value should work out.
This should work, right? But we have to cook up some example. Yeah, is what it is.
Okay, so this by definition is what? Lambda f of x plus 1 minus lambda f of y, right?
Yeah.
So you can similarly
Yeah, Deep,
prove for yeah.
am I audible?
Yes.
Okay, sorry. Yeah, okay.
Second, so this is one way of doing it. The second way of doing it is you'll have to prove this. You'll have to first need to prove f is convex if and only if the epigraph
I was thinking we need the epigraph
is
concept. Yeah.
convex. I mean, we don't need it.
Yeah.
We can still go back to the first principles and do it, but this is another way of doing it. So epigraph
Okay.
is basically all the t and x such that t greater than
Better than
equal to f of
X.
x. Okay, and x belongs to domain of f. So just to let me highlight this. So need to prove this. Okay, and so what I meant is if you have a function like this, right, this pole shaped function, then this is the epigraph. So basically this is your graph of the function. Everything including the graph that is above the graph, this all of this is epigraph. So it's a set, and as you would expect, it looks like a convex set. So that's actually true. Function is convex. The equivalent way of saying that the function is convex is by saying that the epigraph of f, that set, is convex. Okay, so that's what I've written. So if you do this, then what you have to do is then show that epigraph of the max function is convex. So just try it out. Okay.
Yeah. This is a very revealing hint. Yeah.
Okay, so I'll just get started with the questions now.
Yeah. But Deep, I just hello.
Yeah.
Yes, I just clarify from you a point. So you go on with the questions. I just ask you in between. I just pull up the thing.
Okay.
Yeah. So So see, I found the point. So during that previous week's lecture itself, Professor Kulkarni was telling that I'm just reading out what he told, that D is a pointwise minimum of a family of linear functions
Yes.
in the dual Lagrangian,
Yes.
which becomes a concave function of lambda and theta. So in parentheses, he said this does not require the functions f g to be convex.
Right.
So is this more general than? So can we relax the convexity assumptions?
No. So okay, that is simply because x is fixed for a given x. For a given x, it's just a function of lambda and mu, and it's linear in that. I mean, sorry, it's an affine function, not linear. It's an affine function.
It's an affine function. It's an affine function. Yeah.
So for a given x, you
Okay,
have
so
it's just a affine function, and you know that affine functions are common.
okay, this is in general. Okay, yeah.
Yeah, that's all. Anyway, he has proved it also, right? You have seen that.
No, he did not give the proof. No, he did not give the proof.
Oh, I see. Okay, somehow I wrote the algebra in my notes, so I thought he proved it. Okay, but it's so
No,
the thing is, even though it's an infimum, but the argument is going to be very similar to what we have done here.
Yeah. I got it.
So
I got the
just like we
basic
are upper
idea.
bounding, we'll get a lower bound.
Yeah. Okay.
I mean, just to go back to the, so I had minimum of a plus b, right, which will be what? A lower star plus b lower star, right? Because this thing will be greater than equal to a lower star plus b, it will be greater than equal to a lower star plus b star, right?
Yeah.
So it's just I mean, the argument is similar, but hopefully this gives you the idea how to go about it.
Mm-hmm. Yeah. Okay.
And again, because it need not be linear, the function or the minimum function, so we cannot guarantee a strict equality. That's why we keep it as a strict equality. We cannot guarantee that. We just keep it as greater than equal to or less than equal to, whether it's a soup or accordingly.
Okay.
Okay, so assignment 10, question 1. What we have given is t is a descent direction. At some point x0, and we are solving an optimization problem, unconstrained optimization problem. So which one of these is true?
Yeah, just give me 1 second and just pull up the questions.
Yeah, I mean, I'm writing it here.
Yeah, fine. I just got it.
So which?
Yeah, this will be the second option.
And why is that?
Yeah, because the directional derivative should be less than 0, right? For it to be a descent direction.
Yeah, so correct. So one more way to just see it quickly would be, say you have f of x. F of x not. I'm just doing a Taylor series approximation. Let me say. Okay, yeah, this is fine. Not f, sorry. Okay, so if I am in neighborhood of x naught, we are assuming that it's gradients are allowed to be taken, so that means function is continuous. Okay, f is continuous. So then this term goes to 0, the small o term. Okay, so and we want a descent, so what we want is f of x less than f of x naught, right?
Yeah.
So what do we have? This is fine.
Yeah, same thing.
Okay. Question 2.
So just can you go up 1 second, one line, please? Yeah. So when you have neglected the smaller term, it should be in the limit, right? As d tends to 0.
Yeah. So that's why you are using the property of continuity. Meaning,
Right.
sorry, let me, limit, what's happening, I'm not sure. Okay. Yeah, what I wanted to write is limit x tends to x naught, f of x is x naught, f of x naught, right?
Yeah.
So I've just written that.
Yeah, the limiting value is equal to the value of the function.
And same goes for the derivative also. Can apply the same thing for derivative.
Yeah. And when you are saying continuously differentiable means the derivative is continuous, right?
Yes, yeah. But we are not using that here. But what you
Yeah,
said
it's
is
not.
true.
Yeah.
So we have a ellipse here, x square plus 2y square. Okay, it's an ellipse like this. And we are starting from a point x naught y naught, which is 3, 2, and we have fixed the step size of 0.2. So we use steepest descent to get x2, y2. So how do we compute this?
Yeah, so you'll just have to do it recursively, right? You'll have to take one from x0, y0 is the initial point. You get x1, y1 by taking a descent with the step size along the gradient.
Yeah. So alpha gradient f x y. So my initial point is what? 3, 2 minus.
It will be minus 0.2. Yeah, right. It is
This
at the
is
point
very
x1.
important. I'm taking the gradient at the current iterate. Okay.
Yes.
Okay. Yeah, 0.2 times
6, 8,
1
6, 8.
second 2x 4y
Okay.
at 3 comma 2. So I am getting 3 2 1 minus no, this won't work. Yeah, 3 2 minus
It will be minus 6.2. Okay, it's 1.2.
3 into
Okay.
0.4. Okay. And
Uh,
2 into 0.8.
4 into point. Yeah, point.
uh, 2 into 0.8.
This type of This type of calculations are suitable for a computer.
Yeah.
I was thinking of writing a program for doing this.
So we get this, and again just do the same thing. So just to make sure you get the idea of how to present it. So we just apply this same step again, and what's the change here? Hello.
Hello.
Yeah, I think you were gone there for a second. So
Hello.
hopefully you are able to hear me.
Yeah. Just give me a second. Something happened.
So I'll just meanwhile write this step.
Hello.
Yeah.
Am I audible now?
Yes.
Something happened here.
Yeah.
Sorry.
I mean, I'm just writing this algebra. It's nothing really conceptual here, but
Yeah, this is
so the only thing that you need to be careful about is when you're computing the gradient, it has to be at the current iterate. Okay.
Yeah.
Okay. All right. So moving on to the next question. So we have again an ellipse. Oh, okay. All the a's are equal as a circle. Okay, doesn't matter. So 1 by 2. I'll just be slightly lazy. I just write the norm squared, L2 norm squared. Okay. Right. So we have arbitrary initial point. Uh, we do exact line search. Claim is we reach optimum solution in exactly one step. So how do we go about this? True or false?
Yeah, they should be true.
Okay, how do we go about that?
Yeah, so we reason that since the curvature here is constant, by Newton's method, we can take only a single step to the minimum, right? By
Newton's
calculating.
method is not needed. So you can just do this, the following. Uh, so what is the gradient of f at any point xk? Just xk, right?
Just linear, yeah.
Okay. And so okay, let me do one more thing. So let me write this: half of x transpose x. Okay, so q is identity here, right? So what can
Yeah.
I do? F of x plus alpha, uh, f of x, yeah, f of minus alpha. So let me call this gk just for simplicity. Xk minus gk. What will this be? Half xk minus alpha gk transpose k minus alpha gk. So what will this be?
Yeah, it will be xk transpose xk. Yeah, the norm square. Minus plus 1 minus alpha gk transpose gk transpose xk, yeah, and one more term will be there.
This is fine, right? Xk transpose xk minus alpha gk transpose xk. Yeah, this seems fine.
gk transpose xk transpose, yeah, okay.
So how do we find also this is, by the way, this is g alpha. So yeah, slightly sloppy notation, but this g is not the same as this gk, but this is our line search function. Okay, so what do you do? Alpha star is what? Admin alpha greater than 0 g alpha. So what is alpha then?
So this is a convex function.
Okay, so just check
This
it
is
out. This calculation is just a quadratic function, so you can just can even forget this for now if you want. So what you'll end up getting is gk transpose gk by gk transpose gk, which is exactly 1.
yeah, okay.
Why is that? So what did we get? Xk is gk. You put that here. This term and this term is the same. So if you wanted to minimize, these are constant. If you wanted to minimize this term has to be 0.
Okay.
I hope I didn't make a mistake. Let me see. Is there a half here? Yeah, there is a half. Okay. I might have made some algebraic mistake, but yeah, you'll get the your alpha star. I mean, for this step, at iteration xk, you will get alpha star to be 1 to go to xk plus 1. Okay. So yeah, so what will happen? So xk plus 1 is simply xk minus alpha star. So maybe let me put alpha k here. Alpha k star or I can just keep alpha actually, no need to put star. Yeah, xk minus alpha k gradient f of xk, so xk minus 1 times gk, xk minus xk. And what is the function?
Yeah, you're reaching the minimizer.
So in one step it happened, right?
Yeah. Yeah, but by graphing the function also it becomes evident that it's just a quadratic function.
Yeah,
It's
but you have to
symmetrical
still write it. The question is
Yeah,
whether
yeah.
it's one iteration or not. It's not about whether it will reach. So what you need to say is you start at any arbitrary point and you call it xk. The next iteration you will reach there.
Yeah.
Okay. That's all it's saying. Yeah, just check it out. I might have made a mistake here while deriving, but it should come out to be alpha should come out to be 1. Is that
Alpha
fine?
should be 1, right?
Sorry?
Alpha should be 1, right?
Yeah, I think alpha should be 1.
Okay. Yeah, I'll check that out.
Okay, question 4. Okay, for minimization of an unconstrained quadratic optimization problem, so what we have is minimize x in Rn, x transpose qx minus p transpose x, and here q is positive definite. Yeah, q is symmetric and positive definite. Right, so the claim is steepest descent method with exact line search converges faster if condition number of q is close to 1. So is it true or false?
Yeah, it's true.
Okay, and why is that?
Yeah, because it will take a more direct path, right? If the
I mean,
condition number is
yeah, but what is the mathematical justification?
mathematical justification. So I'm not sure how to formulate this thing.
So do you remember this?
Yeah, so when the condition number becomes large, maybe probably the level curves become more distorted.
Yeah, it will
And
become stretchy. Yeah, it will become like
yeah, it
this.
will become distorted.
But if you have something like this, you can just keep going. So let's say this is where your x star is, and let's say this is where your xk is, x0 is. So you can just go straight. But here, because you can start, you end up going like this.
Yeah, means the curvature is not non-uniform, right, across the level curves.
Yeah, I mean curvature. Yeah, in a way you can say that. But here we are also looking at the difference in the eigenvalues. That will. I don't know if you can. I mean, it seems to be a bit more specific than just saying curvature.
Yeah, it's more specific than curvature, definitely.
Yeah. So okay. Anyway, so lambda 1 are the eigenvalues of q. Okay. So and condition.
In any case, if the if Q fails to be positive definite, then the argument, will this work?
No, so in that case, yeah, we'll have to, what we can do in that case. So if Q is negative semi-definite,
Yeah.
then typically, I mean not here, but actually negative, strictly negative definite is also fine. Just invert the sign and you'll get what you want.
Yeah.
But in general, maybe you can come to Newton methods, and probably it will make sense there, because in case of Newton methods, so we need H inverse, right? So which
The
will be
Hessian.
Q here.
Yeah.
I mean Q inverse. So we will construct Sk at each iteration such that Sk is roughly Q. Sk such that Sk inverse is roughly the Hessian inverse at each iteration. So there are methods to do that, quasi-Newton methods.
The BFGS and all those, right?
Yes, yeah.
Okay.
So what you can do is at every step you'll have to construct another matrix which roughly mimics this inverse Hessian.
Okay.
But then that means you'll need update equations for these Sk also.
Yes, at every iterate, right?
Yeah. So it becomes
So
expensive.
how are they, how these methods, second order methods, are computationally feasible for present machine learning optimization problems? I have rarely seen them, the second order
Yeah,
methods.
it's generally expensive. People don't use it. People just use first order methods.
Okay. So then in which use cases are they used more extensively than in machine learning? Any?
Machine learning also sometimes it is used. I mean, just an aside, it called something called natural gradient descent.
Okay.
But I don't know at scale how many of these things are
Yeah,
used.
that's the point. At scale, it's
So you can just look up maybe natural gradient descent, but that will be a digression from the discussion here. So
okay. Natural gradient descent.
yeah. So yeah, just to come back to this comment here. So what I meant to say was, when you say curvature, it's not really specific. You just talk about the matrix, the Hessian, which in this case will be Q. But when I said specific, what I meant was we are looking at these ratios of the differences as sums of these least and the smallest and the largest eigenvalues. Okay.
Yeah,
So
yeah.
if you specify the Hessian, then obviously you have also specified the lambda ones and the lambda n's.
Yeah, yeah.
Okay. Right. So this condition number is basically the ratio of the largest eigenvalue to the smallest eigenvalue. So he skipped the proof, not a proof really, it's just a bit of algebra. So do you
Yeah,
want to see the
he
algebra
stated,
for this?
he stated the theorem without a proof. Yeah.
Yeah, I mean, so here in this particular case at least it's not, I don't know if you can call it a theorem, but yeah, maybe I'll just write a few things about how to regarding how to go about that, specifically for this quadratic function. Otherwise we can skip. Hello.
Yeah, yeah. Tell me. Yeah, am I audible?
Yeah. So do you want?
Yeah,
to give...
you can give some explanations further, because I have just written down the statement of the theorem or whatever he stated, but without any further comments.
Okay. Okay, fine. So yeah, we'll just take a slight detour and look at these calculations. So right. So let's just set up terminology. So xk plus 1 is xk minus alpha k gk. Okay, my error term at xk will be f of xk minus f of x star. So I'm just defining these things. Okay, and so what exactly is error? The error term? It's basically half of xk minus x star transpose q x minus x star. So the reason is simply that here, if you put the first order necessary condition, you have qx star equals to b. So that means when you put that, x star transpose qx minus b.
This vanishes, right?
Yeah, that's all. So that's why we have only the rest of the terms.
Yeah, yeah.
I mean, I can just write it like this. That's what I'm trying to say. Okay.
Yeah.
Right. So yeah, let's just get started. So we want to look at what happens. So what we are really hoping to do is error at xk plus 1 if it can be bounded like this. That will be nice.
Error at xk plus 1 is okay, some constant
Yeah,
less than
it's like basically I'm saying I'm
okay.
inching closer towards f of x star.
Okay.
Okay.
So b should be less than 1, right?
Yeah, we will see. We'll see at what rate it does.
Okay.
Okay, so let's write exk plus 1. So that will be by definition xk minus alpha k gk minus x star transpose q, the same thing. Okay, and let me call xk minus x star as just yk, because notation will become a bit clunky very soon. So what can we write? Half of yk minus x star transpose q yk minus x star. So let's just expand it. So what we'll end up getting is yk transpose q yk minus 2 oh sorry I wrote the other way. Half of yk minus alpha k gk transpose q yk minus alpha k gk. So what I get is yk transpose q yk minus 2 alpha k yk transpose q gk plus alpha k square gk transpose q gk. Okay. So what do we get? So we'll just take this term out and we'll see if it will simplify a bit in 1 or 2 steps. So 1 minus alpha k square gk transpose q gk plus 2 alpha k, maybe careful about the minus sign. Yeah, there is a minus sign here also. So anyway, so plus 2 alpha k yk transpose q gk. So far so good. I mean, I'm just expanding the terms. I have not done anything new.
Yeah. So there are 2 minus 1 in front of other.
Yeah. I'll just shuffle that term. I just forgot that there is a minus sign there. So what we will do is we will put that value of alpha k. So for this case, for these quadratic functions, if you I think I've already written that somewhere. or maybe I erased it. Oh no, it's here. This one, alpha k will be gk transpose gk by I'll just let me write it down. So for our function alpha k will be nothing but gk transpose gk by gk transpose q gk. Is this fine?
Yeah.
Or do you want to derive it?
No, it's fine.
I mean, it's just writing the same thing like I was saying before. I just write down this.
Yeah. The function from the functional form itself, it will become evident.
Yeah,
right?
there'll be extra q here.
Yeah.
So that's about the only change.
Yeah. Exactly.
So you get a q here, and so yeah, it will be clear from there. Right. So okay, what else? Yeah, so we'll just put this alpha. We'll put this alpha.
The expression will simplify probably after that.
Yeah, you can anticipate these kinds of terms
Yes,
getting
yes.
cancelled out. So
Precisely.
it will still be a bit lengthy. It won't be completely straightforward, but yeah. So what we will get is yk transpose qyk 1 minus, yeah, so I just swap the terms so that it's less confusing. So minus 2 gk transpose gk transpose q gk yk transpose q gk minus gk transpose gk whole squared gk transpose q gk and gk q gk squared. So yeah, you can see it immediately becomes clunkier, but yeah, in a few steps it will simplify a bit. So far again I just did one change, which is I substituted the exact line search, the alpha k that we get from exact line search.
Yeah.
And just an aside, yk is xk minus x star. Okay, so qyk will be what? Qxk minus qx star. And what is qx star? B.
Okay.
So
okay,
qyk
yeah,
is nothing but our gradient.
Okay.
So I'll denote it by gk.
But this is falling out from the special case of this being a quadratic
Yeah,
function.
yeah, of course, yeah. I mean, otherwise it's I cannot write any of this.
Yes.
Okay. So what where is that term? Anyway, yeah. Let me continue to simplify, and you'll see how these things are being used. So by the way, what is this by our definition? So what is ek? Sorry, e of xk is this, right?
Yeah, e of xk.
So and what is this term? Just yk.
Is yk. Yeah.
So this is our error at xk.
Yeah, e of xk. Yeah.
Okay, so one thing is done. So now we have to simplify this mess and see where it takes us. Okay, so yeah, so by the way, we will use the fact that qyk is nothing but gk. So what do we get? 1 minus 2 gk transpose. So yeah, I'll just keep this here. Just simplifying this term here. So remember Q is symmetric, and so QYK is nothing but GK. So that means in the numerator here I have GK transpose GK, and this is also GK transpose GK.
Yeah, that will cancel out.
Not cancel out, it's just a square.
It's square. Sorry, it's square.
Okay, and did I mistake somewhere? Let me see. Oh, I think I'm mixing up signs. Okay. Okay. Let me go by the order. Let me not mix up things. Yeah. So we are looking at this term. So what are we getting in this? Oh, I think what I had written was correct. I think
Yeah, it was correct. I think the sign may be a little off. I don't know.
No, this is fine.
It's fine. Okay.
Yeah, this is fine. Right. So here, what will happen is this term gets cancelled because there's a power of 2 here.
Yes, one will get cancelled. Yeah.
Okay, and YK transpose QYK. So basically, what we have gotten is error times 1 minus GK transpose GK whole squared, and GK transpose QGK, YK transpose QYK. Okay, and so here cos QYK is GK, and I can again use this fact. I can write. Yeah, sorry. Yeah.
Just hold on for a second. Just go one line up. So -2 -1.
So let me put
yes.
this here.
Now it's correct.
Okay, so again I will use this info, but I remember Q is a positive definite matrix, so Q is invertible. So I can say YK. So
it's
what?
Q inverse.
Yeah, Q inverse. So what I can write now is 1 minus GK transpose GK whole squared. GK transpose QGK, GK transpose Q inverse GK. So this QYK I have written as GK, and this YK I have written as Q inverse GK. Okay, QYK is GK and YK is Q inverse GK. So I hope
Q inverse squared means two Q inverses would come now.
No, this Q is used here. QY is giving GK.
Okay.
And the remaining YK is giving me Q inverse GK.
Okay.
Okay, so what I get is 1 minus gamma k exk. So where this whole thing is 1 minus gamma k. Okay, so actually we would like to find minimum gamma k such that exk plus 1 less than equal to b exk. So what you end up doing is you end up formulating an optimization problem to minimize this whole term, which is equivalent to saying you maximize this term.
Yeah.
So that's going to get a lot complicated, and so yeah, I think I will for now skip it, but we can return to it later if you like. And so when you optimize this, right? So when you end up gamma min will actually look like 4 times lambda 1 lambda n lambda 1 plus lambda n squared.
Oh, so this involves the eigenvalues.
Yes. So yeah, you'll have to use the properties of Q here.
But you can do by plain matrix calculus, right? That one, that minimization.
There is no matrix calculus needed. It's just some basics of linear algebra. I mean, you won't even need that one.
Okay.
Yeah. So just the fact that Q is symmetric and positive definite will let you derive this. But yeah, it will take maybe 10 more minutes to solve this.
Okay. Okay.
Or maybe more. I'm not sure. So when you plug this gamma, so plugging this gamma min, we get the expression that you saw in the lecture, exk plus 1. So here we are looking at the norms squared, so that's why we are getting terms like this, lambda 1 minus lambda n squared by lambda 1 plus 1 minus 4 lambda 1 lambda n lambda 1 plus lambda n whole squared exn, and this is nothing but lambda 1 minus lambda. Okay, if you like, I'll write the other way around.
Yeah, it's lambda 1 minus.
Okay, so yeah, I mean it's slightly long. It's not technically straightforward, but yeah, this allows us to do this.
Yeah, but in the class he mentioned a more general version probably. He just mentioned f need to be twice continuously differentiable, and then everything will follow.
So once you prove this, it's very straightforward to do that, because you can just look around your minima. You can just construct a neighborhood around your minima. It's already twice continuously differentiable there. You can just do a Taylor series expansion.
Okay.
Look in that neighborhood and apply exactly this result, because once you've approximated the function quadratically,
you apply your approximation locally. Yeah.
So basically this is what you need to prove.
Yeah.
Okay, so I just thought that So I just thought that he skipped this analysis, and so just try to fill in the gaps a little bit. Try this out.
This is good. This is good. Helpful.
Try this exercise, right? So as of now I have only told you that exk plus 1 is some multiplicative factor times the e of xk, right? But really what we want to do is we want to get an upper bound.
Okay.
Right, so this is what I skipped, right? So might be instructive to just play around.
Yes, definitely. But you just need linear algebra, right?
Yeah,
you do not need any calculus for this.
Yeah, I think it should be fine. I mean, I don't recall the exact steps right now, but should be doable. I don't think you need any advanced
steps. I'll give a shot at it. Let's see.
Okay, and if you have some doubts, you can ask me next week. Okay, I will come back from this detour then. So wait, did we answer the question that we set out to ask? Yeah, okay, true. So kappa close to 1 means xk plus 1 minus x star is roughly 0. Okay?
Yeah.
Alright, so yeah, I think we have answered this question. Let us go to the next question,
So
which is
this is why you need preconditioning of matrices, right? To speed up these things, right?
yeah. So right. So you may want to correct. You may want to improve the conditioning by, let's say, adding lambda times identity matrix and shift the bump the eigenvalues appropriately.
Yeah. Okay. Yeah.
Yeah, but apart from shifting it to above zero, I don't know if there is a method to space out the eigenvalues, because then that will deteriorate the curvature of the.
Yeah. In a sense, yes. In a
So
sense, yes.
I don't know. I'm not sure. What
But
happens
generally,
if.
the numerical optimization things, I generally they start with preconditioned gradient descent rather than pure vanilla gradient descent.
So just to make sure I understand, when you say precondition, what do you mean?
You means you apply a preconditioning matrix so that the eigenvalues become this thing. Just hold on.
No, are you talking in the context of inverting matrices?
No. I'm talking in the context of gradient descent only. Gradient descent.
No, that's okay. But conditioning generally is about, like I said, this gap between lambda n, the largest and the smallest eigenvalue, right?
Okay.
So conditioning is about, so ax equals to b. I am
Uh-huh.
hoping that if I end up, let's say, coming up with some delta x, I mean, sorry, I end up arriving at a solution x plus delta x instead of x.
Mhm.
That will give me some b plus delta b, right?
Yeah.
So I am hoping for my delta b by b to
Yes,
be
yes.
very small.
Yeah. I understand where you are getting at. Yeah, but I'm talking in the context of this thing, this gradient descent only.
Yeah, but I'm not sure what preconditioning means there. I mean, this is what we mean by the
No,
conditioning
you
of us.
just change your variable so that the curvature becomes more symmetric, like a spherical kind of thing. That is what I was meaning.
I mean, what you are saying sounds more like a convex approximation of a problem in a neighborhood and just
No,
solve that.
you do what you call the Cholesky factor and all those things.
But Cholesky factorization is only for positive definite matrices.
Yeah, for positive definite matrices,
So
true.
if you already have positive definite matrices, that means that it's a convex. I mean, well, it's not a convex, but at least in some neighborhood you can approximate by a quadratic function. So which is having that positive definite Hessian. So okay, I'm not sure. Maybe you can discuss this offline. I'm not
Yeah,
sure, but
yeah, yeah,
but
yeah.
conditioning, when
Please.
you said, this is what came to my mind. So
Yeah, that is the pure classical. Yeah, that I understand. This conditioning, how much sensitive is the error is to an approximation. Yeah,
yeah,
but
okay.
I'll talk you. I'll get to it offline probably. Yeah. Right.
Okay, so the next question says that I have a sequence which is basically geometric. I mean, 1 by 2 to the k, and question is, what is the rate of convergence? So how will you find the rate of convergence?
Yeah, this is just by applying the basic definition of this thing, right? This.
So what is the definition?
Yeah, I'm trying to get that. Forgetting that. Just
Okay, so what is the limit of this?
limit of this is 0, right?
Yeah, it is 0. So yeah, here x star is 0.
This definition was a bit confusing for me to first time to understand this.
Uh, okay. Uh, I mean, just keep this fact in mind. Ultimately, what I want to say is, if I am at a certain point, xk, let's say, and let's say I had a way of measuring my how far I am at this point xk, where I am right now, from x star. Let's say I had a way to measure this distance. Okay. All that
Okay.
I'm saying is, if I take a step along some appropriate direction, how much closer am I coming to my x star compared to how close I was before at xk?
Yes.
So that's
Understood.
all I'm saying. I'm just saying, when I take these steps xk's, I just take a ratio of this. I just roughly want to characterize this constant beta.
Mhm.
Now,
Okay.
I mean, here I assume that this power is actually 1, but actually it can be anything. So what I
Okay.
really want is an idea of, okay, as a as a function or a power of distance from xk to x star, of course. What is this constant beta, and for what alpha do I get that constant beta? That's all I'm saying how fast I'm going to x star. Is this just one way of measuring it?
Okay. Okay.
Okay, so here we have only
By any
scalars.
means, so yeah, is x star here the limit point of the sequence?
Yes.
Okay.
So what will it be? Limit k tends to infinity 1 by 2 to the k plus 1 by minus 0, 1 by 2 to the k minus 0. So what do we get?
It will be half.
Okay, so that means,
Beta. Okay.
so rate is linear, right?
Yeah, rate is linear. Yeah.
And why is it linear?
Because that alpha is 1, right?
Yeah, so this alpha is 1. All right. Question 6. Again we have quadratic function of x transpose qx minus p transpose x. As usual, we will take the q to be symmetric positive definite matrix. Starting from, yeah, so we start from some x naught arbitrary initial point, and claim is Newton's method will converge to optimal solution in single step. This is true.
It's false.
Okay, why is that?
Yeah, because it should satisfy some sufficiency conditions, right, of Newton's. You cannot say this without qualifying.
No, but I didn't get you. What when you say?
No, I am telling we need some sufficiency conditions like Newton's method to converge, right?
No, but we are not saying any arbitrary function. We are taking this quadratic function which happens to be having a Hessian of positive def. So we know that this is a convex function.
Yeah, but as we saw that if the curvature is varies from place to place, then we may not converge in a single step, right?
Okay, so let's just then write this down. So how, it's a convex function, right? This much at
Yeah,
least
it's
you
a
agree.
convex function. Yeah,
So
it will converge, but we cannot guarantee it will do it in a single step from the matrix Q, right?
okay, anyway, so let me just go step by step and see what happens. So f is convex, and that's because the Hessian is q, which is positive definite, right? That's the definition of convexity.
Yeah.
Okay, so what else can I say? So then in that case, if I say gradient of f of x star is 0, so this implies x star is the minima, right?
Yes.
And because it's convex function, that means the local and global minima are the same,
Yes.
right?
Yes. Yes.
Okay. So local, global doesn't matter, it's the same because it's a convex function. Okay, so what is the gradient here? Qx minus p, right?
Qx minus b.
Okay, so therefore Qx star is b, and Q is invertible, so x star is uh, Q inverse b. And just in general, gradient at any point x, I'll just write it down for completion, Qx minus b, right? Which is nothing but Qx minus Qx star. This is nothing but Qx minus x star. Is it fine?
Yeah.
Okay. Right, so what else can I do here? So okay, what is the Newton's method? What is the Newton step? So let's say I start at x0 and I want to go to x1. So what is the direction that I have to take?
So you need to solve the Newton's equations at those points, right?
There are no Newton's equation. I mean,
Yeah.
Newton's step is, just to recall, xk plus 1 is xk minus the Hessian at the point xk. Take the
Yeah,
inverse
that
of
is
this.
what I mean. Some people call that Newton's equations at that point. That's it.
Okay.
That's
I
all.
mean, so we're just updating. We are not really solving any system. Maybe here you can say you are solving a system of equations, but here we are just updating it.
Yeah, it's a misnomer. Yeah, in a sense. Yeah.
So what is the Hessian for our case?
Hessian is Q, right?
Q, right? So that means here you put a Q inverse, and the gradient is simply the GK, right?
Yes.
GK, which is nothing but this.
Yeah.
Okay, so then what do we have? So this is Q inverse times the gradient of gradient at x0, right?
Yeah. X0, or you can put it xk as xk plus 1. Anything is fine.
Yeah, I mean it's okay. I hope it's clear from the context.
Yeah,
Right?
it's fine. It's fine.
So what do we get? X0 minus Q inverse Q x0 minus x star.
X star. Yeah.
This thing is identity.
Identity.
So x0 minus x0 plus x star.
So you get an X star.
So does it reach in a single step?
Yes.
Yeah. So in a way it's expected, right? Because I am using the curvature, so I should do at least not do worse than the steepest descent.
Yes.
Right. So it is true actually. So we don't need to. I mean, at least in this case, the point is it's a convex function, convex
Yeah.
everywhere.
Yeah.
So I don't have to worry about the curvature leading me astray.
Yes. So whenever you have convex function, if you use Newton's method, you are guaranteed to reach in a single step. Can you say a statement like that? Not necessarily, right?
So here, like I'm saying, so it depends how good this quadratic function is an approximation of your actual function in the space or in the domain of the function where you initialize your iterate.
Okay.
So if it really closely matches this behavior
Then
where you
it's fine,
initialize,
yeah.
then you're good
Then
to
it's
go.
fine. Yeah.
I mean, just simply if I just draw a thing like this, if you start here, it's fine, right?
Yeah.
But if you start here, I don't know. Okay, here also is fine actually.
No, you take something like a tan inverse function, then it's a bad thing near the origin. You use Newton's method.
I mean, yeah. The point is, you got right from what I
Yeah,
tried.
I got this. This is what the sufficiency condition means, right? In the case of Newton's.
Yeah. So if my quadratic approximation is good,
Yeah.
for my actual function that I'm optimizing, then I'm fine. So claim is that for unconstrained optimization. So we are talking about unconstrained optimization. If Newton's method converges, always converges to local minimum. So I mean, anyway, I wanted to discuss this, and that's precisely the next question.
Yes. It's a coincidence.
So yeah, we are doing unconstrained optimization, and we are using Newton's method, and let's say we are using Newton's method, and the claim is that it always converges to a local minimum. So is this true or false?
So it should be false, right?
Okay, so when you say false, then we need to come up with a counter example.
Yeah, means just give one example I was suggesting is you take the tan inverse function. arctan function near the origin, and it can be easily shown that if x0 is not a properly chosen point, it will diverge, keep on diverging.
So you are saying something like this.
Yes.
Can you repeat the argument? I didn't get you.
So I was saying, if you do not initialize it at a proper point, suppose not near the origin,
Right.
somewhere in the middle of the slope region, then it can be easily seen that the tangent line will diverge.
Are you saying here?
The points that, probably a further up, probably a little bit further up.
Oh, okay. Here?
Yeah, somewhere around here. Yeah, that should be okay.
I mean, this also, why is it not fine? So
Yeah,
I'm going
that,
like
that is all
this,
that.
and then so my rate of change of derivative is decreasing, right?
Yes.
Okay. So we are saying I'll end up ascending instead of
Yes, you'll get
descending.
a ascending. Yes.
Okay. So but if I was here, I would be fine. But only because I'm
Yeah, it
starting in
was
this
sufficient.
concave region, it's a problem.
Yes.
Okay. So we can actually construct a example. So I mean, here also we have not written anything. So let's just write a simple enough example that we can quickly show the the steps. Okay. So in general, like you said, in general, uh, Newton's method converges to stationary points which includes saddle points also.
Yeah.
I mean, you can just probably do this x cube. I think if I start here, it should be fine, but if I start here, I think it will be a problem. Okay, anyway. So we'll just construct a simple example. We'll just take a 2D case, x square minus y square, a very simple function. Just took two quadratics and just subtracted them. So what is the gradient here? 2x minus y, right? And what is the Hessian?
Hessian is 1 minus 1. Sorry.
Yeah, I mean, except for the scaling, it's fine.
Yeah.
So the inverse will simply be 1 by 2, 0 minus 1 by 2. So what do we get? x1, y1. Let's say we start at some x0, y0. And what's the gradient? The gradient is 2 times x0, y0. So what do we get? 0, 0.
Yeah.
Because I mean, this 2 simply gets cancelled out here.
So this is a counter example right here.
Yeah, so this is a saddle point, right?
Yeah, this is a saddle point, definitely. Inflection point here.
So, but 0, 0 is not a minima. What is a minima here? Minus infinity, right?
Minus infinity.
So, it's not a minima, it's just a saddle point. Okay, question 8. So dwelling a bit further on this limitations of using Newton's method. So what are the drawbacks of Newton's algorithm? If you were to name a few. Can you name a few?
Yeah, the starting point. Yeah, you need to be. The algorithm is dependent on the starting point strongly.
Yeah, depends heavily on initial point, right?
Yeah.
Right. And what else? What other thing you could anticipate?
Yeah, the Hessian needs to be in the equation. The Hessian comes up, right? So you need to get invertible at every iteration.
So this just goes back to the earlier point I had, right? So if Hessian is not invertible, I need to construct an approximation for the inverse of the Hessian at every iteration. We can do
Okay.
that, but then that again incurs a lot of cost because we need to constantly
Yes.
keep coming up with these approximations of Hessian at each iteration. And why can't we just do so? When I said Hessian, right? So why do we need to approximate the Hessian at each point, at each iteration? Why not just do it once in the beginning and then let it be?
Yeah, because this is a local thing, right? You have to convert it every point locally, right?
So what I wanted to bring out was this is actually a function of xk,
Yeah, this it is
the
yeah the
current
right
iterate. Okay, so actually it is hk.
HK.
In our case, because we had a function of the form x transpose x and some minus p transpose k, whatever we discussed earlier, the Hessian of xk is q
Just Q.
for
It's
all k.
just yeah does not depend on X.
Okay, so just to clarify that.
So how do you calculate approximate it by the all those algorithms like BFGS and all?
Yeah, so you'll have the BFGS methods. Right, so just to complete this, okay, so A and C are correct. In the next question, we are given a constraint set. Okay, so this is our feasible region of an optimization problem. G is continuous. Uh, Question is which can be used as penalty functions. Okay, so let me write the option and then we'll just recall the definition and definition of
Yeah,
penalty
we need to
function, and then
recall
we
the
can
definition.
answer this.
Yeah. So in the context of this question, I just wanted to ask you. So,
Yeah.
Prof came up with penalty function definition. So are they canonical or there are others also, many others also?
I am not sure. I mean, those are the ones that I have commonly seen.
Okay.
Yeah. But other than that, I have not seen. Yeah, so okay, so what is the definition of penalty function?
So that function should be continuous.
Okay, so penalty function, let's call it P. So P should be continuous.
It should be greater than equal to 0, non-negative,
Okay.
and Px is equal to 0 if and only if x belongs to S, feasible set.
Okay. If and only if x belongs to feasible set. Okay, yeah. Okay, so right, so this is the definition. So so what do we do? So what is our constraint? G of x greater than equal to 0.
Yeah.
So does this one make sense? Norm of g of x?
No, non-continuous, right?
Norms are continuous.
No. Sorry. P is continuous. Yeah. greater than equal to 0. No, wait. So A means if x is greater than equal to 0. Yeah, this is continuous.
So the third condition gets violated.
Yeah, third condition. Sorry. Third condition is violated.
Because even if it's in the feasible set, it can still g of x can still be non-zero, in which case the norm
Yes,
can
yes.
be non-zero, right?
Yeah.
So A doesn't make the cut. How about B, minus of min g of x 0?
Yeah, this is negative, right? For the feasible region.
For the feasible region, g of x is greater than equal to 0, and hence the min is 0.
Yeah. Min is greater than equal to 0. But yeah, this.
Okay, so let me just write down. So is it continuous?
Yeah.
Is the min function continuous?
Min function. Yeah, it's continuous.
Okay, I mean could be continuous. We don't know for sure because we don't know the g.
Yeah. Yes.
Okay. What else?
This is also greater than equal to 0. That is also true.
By the way, what I said, I was just checking. So, P is continuous. I don't need any condition on G, right?
Yeah, because it's the minimum, right? Just from the definition. Yeah, G says greater than equal to 0.
It's greater than equal to 0. I'm not getting any discontinuities.
Yeah.
Okay. Right. So, okay, P is continuous. What else? It is clearly. Is it greater than equal to 0 for all x?
Yeah, it's not strictly greater than 0, but it's equal to 0 also possible. So it's never less than 0.
No. Let's go to the third condition. Sorry, not sure what's keep happening. So let's come to this later. Let's just focus on this px greater than equal to 0. Is it non-negative? So g of x could be in general negative, right?
Yeah.
So g of x could be in general negative, but then there's a minus sign.
Yes, then it flips the sign. Yeah.
And if it is non-negative, then anyway it is 0.
Yes.
So then it is greater than equal to 0.
Yes.
What about p of x being 0 if and only if x in S? So let's see. So if x is in S, then the minimum of this is, the value that this function takes is 0, correct? Because g of x is equal to 0 and this minimum is 0.
Yes, it's 0.
If this is 0, in that case, what can we say?
If this is 0, yeah, then gx must be less than equal to 0.
So if it is less than equal to 0, then this will be some non-zero value, right? Non-negative, some strictly positive value. So actually the only possibility is gx is greater than equal to 0. Which means that if this is 0, that means x is in S.
Yes.
Right, so this is true. This is a candidate. Okay, similarly, what about this? G of x minus alpha squared for some alpha greater than 0. So is P continuous? P of x here?
It's continuous.
It's also greater than equal to 0, right? For all x.
Yes.
But what about this? P of x being 0 if and only if x in S?
No, this doesn't hold.
Okay, it's clear, right? So
yes,
the only way it can happen is this g of x is exactly alpha.
Yeah.
But S contains all such that for all alpha greater than equal to 0. This is
Yes.
for some fixed alpha greater than 0.
Fixed alpha. Yeah.
Right, so this doesn't work. Okay, what else is there? Max of g of x comma 0. So here is p continuous. So g of x is, remember, greater than or equal to 0.
This thing also continuous.
Yeah, and so g is continuous, and we are just taking max with max of g of x and 0, right? So p is continuous here. Is this greater than or equal to 0? So g of x,
Yeah,
we
that
know
is
that
also
is greater
true.
than or equal to 0, and this is 0. So
Yeah, that.
we know that this is greater than or equal to 0 for all x. Okay. But what about this? So let's say p of x is 0. So that means that g of x was 0. So which means that x is in the feasible set by definition, right?
Yes.
Okay.
But we have to go the other way also, right?
Yeah. So which way we went right now? We said if this is 0,
This is yeah.
then this
it
is
belongs
fine.
to the feasible.
But what about x belongs to s? Let's say x belongs to s, and let's say g of x is not 0. Then this is not 0, right?
Yeah, this is not.
So this is again not true. Okay, is that fine?
Yeah, it's okay.
I mean, this is really the one of the defining traits, right? You want 0 penalty when you're in the feasible set. These clearly
Yes,
fail
yes.
to offer that.
Yeah. Because by definition, you do not want any penalty when the point is feasible,
Yeah,
right?
yeah. You want the if and only if to hold true. Okay, so last 3 questions left. Let's look at again another quadratic function, but in 2 variables. So by the way, if I want to write this in terms of a matrix vector product, how will I write this?
Yeah, this is just you take as a q as diagonally half. Yes.
Okay. So we are optimizing using steepest descent method. Alpha is, let's say, 0.5. So alpha k is 0.5 for all k, fixed step size. Let's say we are starting from this point, which is 1 1. Question is, how many steps needed to converge to optimal solution? Exactly. So how would you go about this?
So since you are not reducing the step size, it will just keep on zigzagging, right, without converging.
There is no zigzagging here, right? Because both the lambda are the same.
No, but even if it's not zigzagging, you need to decrease the step size over iterations, right? Otherwise,
Why
it will
do
just
you
keep
say that?
oscillating, right? Otherwise, it will just keep oscillating because I was just doing a counter example by drawing a quadratic function in one dimension and thinking about this thing.
Okay, so that is, I think you are getting at some other point. So maybe let me complete that thought. I hope this is what you were saying. So if you start with f of x as x square, right? And let's say you take step
Yeah.
size as 2, and let's say you
Yeah.
start at 1. And let's
Yeah.
say xk plus 1 is xk minus alpha times 2xk, which is
Yeah,
nothing
it's
but
just the
minus xk.
gradient is here. It's just the sign of
Yeah, but so
negative the
that
sign of x.
this is to do with the Lipschitzness, okay? So
Oh, the Lipschitz continuity.
yeah, so here what that the point, I mean, from what I understand, that example is a good illustration to say you should be careful about your step size, even if you want to keep a constant step size. At least in this case of quadratic function, you have to have alpha, the step size less than 1 by L, where L is the Lipschitz constant for this function f. Okay,
Okay.
but that's something we don't need to allude to those things here. We can do something much simpler,
Okay.
and that is just simply
Oh.
writing the iterate equation. We'll immediately get to know what's going on.
Okay.
Okay, so what is the gradient here?
Gradient is half, right? Hey, sorry. It's uh,
So
it's
gradient is nothing but
half half xy.
yes. And what is xk plus 1? Xk minus alpha gradient xk, because you're using steepest descent with alpha k as alpha, and alpha is nothing but
Yes.
0.5.
Yes. So here it
There should
is.
be another 2 here. I forgot.
Oh,
So
that is
this
square,
2,
right?
yeah, this is square, right? So basically x
Yeah.
and
Yes.
y. So it's just
X and Y. It should be X and Y. Yeah.
so I'll just remove this. So what is this xk? Okay, I think I should have. Okay, wait. So xk plus 1 by k plus 1 is xk yk minus alpha gradient f k yk. Fine.
Yeah.
So what is this in this case? Xk yk minus half xk yk, which is nothing but half xk yk.
Yeah. Yeah. So this doesn't.
So what is the optimal value here,
It's 0.
and when is it attained?
Yeah. K is equal to infinity as K tends to infinity.
Yeah, so optimal value 0 at 0 comma 0, right?
Yeah.
So let's say you need infinite steps to reach 0 0 from 1 1, right? Okay, we again have a quadratic function. So by the way, how do we write this again in a matrix vector form? Matrix vector product form.
Okay. This one. Okay. One. Yeah. It should be 5 or 1. Yeah. Then it's 3. Then it's 1. Yeah.
I think this will be the case. Okay. Anything else? Is an expression
No.
correct?
These are quadratic form, right? We have remaining terms plus. Yeah. Plus 0, 6. Is it? Yeah. 0, 1. Yeah. Plus 6. Yeah.
Okay. So actually a lot of times this itself simplifies your calculation. So I'm just writing that here. Others you have to, yeah, it's just a bit convenient to write it compactly like this. So question is, which of the following is not descent direction for f at point 0, 3. So the options are 0, comma minus 1, minus 1, comma 0, 1, comma minus 1, minus 1, 1. So how do we check this?
So you take the gradient of that function at 0, 3.
Okay, so but
And
principally what do we need to do?
you take the gradient direction and you take the inner product with D, the direction D, and see which decreases the function.
So we want this to be?
Less than 0.
No, it has to be not a descent direction.
Okay, it's not a descent direction. It's greater than 0.
Okay. Which of the following is not? Yeah, it's not a descent direction. Yes.
It's greater than 0.
Yeah. Okay. So what is the gradient here? So more like xk yk. So what's the gradient?
Yeah, gradient will be
2qx minus b.
Okay, qx minus b. Yeah. Okay, that's the answer.
So this is q.
Yeah.
This is b. This is c.
Yeah.
So what do I get if I take the derivative?
Qx minus b.
See, it is x transpose qx plus b transpose x. Okay, I'm writing x, but I hope you see that it's a vector. So what will this give? 2qx plus b. Is it fine?
Yeah, it's okay.
So 2q xk yk plus b. What is q? 5113, and what is b? 01. 5113. What is xk yk? Is it given? Yeah, xk yk is given to us. 0, 3. And what is b? 0, 1. So what does this give us?
0 is 3, so it's not. First is 3, then it's 10. 310, right? No, okay, 9, 6. 6, 9.
5, 3.
Okay.
Yeah, I think this is fine.
Yeah, it's okay.
So basically I have 6, 19 as my vector. I want D such that the value, the inner product is positive. So D seems to be fine.
Yeah, D is given. So 0 minus 1. So that is not true.
So I just calculation.
Yeah, it's fine. It's okay.
Question. Okay, last question. Consider the statements and choose the correct. Okay, so statement number 1. Just give me a second. Yeah, sorry. So statement 1 is saying each iteration of Newton's method is computationally heavier than each iteration of steepest descent. And statement number 2 says that convergence rate of steepest descent is faster than that of Newton's method. Yeah, so yeah, which one is true, which one is false?
Yeah, statement 1 is true.
Okay, statement 1 is true
Because it requires more calculation than the descent method, right? Steepest, because you just need to calculate the gradient for the later case, and here you need to calculate the Hessian also.
yeah, so yeah, there's one straightforward. So this is something we did not prove. I am not sure. I don't think we can do it now since you're almost out of time. But this is a fact that statement 2 is also true actually. Sorry, statement true. Statement 1 is sorry. Statement 2 is false. So we didn't see the proof yet, but Newton's method has a quadratic convergence rate.
Yeah, the proof we didn't see.
Okay, whereas steepest descent we saw, it is a linear convergence rate. Okay.
Yeah.
So maybe I don't know. I'm just wondering if I could maybe put one or two more questions about Newton's method. So give me a minute. I'll just take a look at my notes. Meanwhile,
Yeah, sure.
just go through your notes and let me know if you have any questions about the discussion so far.
No, I was just a little bit unclear about Wolff's condition. Means the first condition was fine, but the second condition I was a bit unclear about. So, anyways, we may clarify it in the next class if you have time.
We can talk now also. I mean, so are you talking about the proof for it or just the intuition?
No, not the proof. Actually, what the statement means. Before the proof, I just want to know what the significance of the statement itself.
So, okay. So, are you saying, okay, let me maybe go to a new page. So, if I have, so let's say if I had something like this. Okay, yeah.
Yeah,
Right.
just give me 1 second. First rule condition. Yeah, the second rule condition. Yeah, it relates to something the sufficiently decrease, right?
Yeah, so you want to do two things. You don't want to take too big a step size, and at the same time, you don't,
Yeah.
because that will not perhaps yield a sufficient decrease in the function value. At the same time, you also don't want to take two. So, okay, let me just finish this drawing. So, for example, the first condition said, okay, you so which means do I want this? Yeah, okay, sure, fine. So So this region is fine. Similarly, this region is fine. So okay, I should have completed this. So this is the first condition, right?
Yeah, this is the first one.
So here I said that the slope is c1 times g dash 0, where 0 less than c1 less than 1. Right. So but then the risk is I could just, so you can see my cursor, I hope. Maybe let me change my color. Okay, blue is add one. Is the green color maybe somewhat better to see?
Yeah, it's visible. It's better. It's okay. It's fine.
Okay. So if I start from here, I can, this is all an acceptable region, right?
Yes. Yes.
So
Yes.
maybe I just ended up going somewhere slightly here. That's all. Not much.
Okay. Okay.
Uh, right. So I didn't want to take too small a size as well. Okay,
Okay.
1 second. My pen ran out of charge. 1 second. Okay. Yeah, just give it a minute. Can I use my
Yeah,
hand?
it will just charge in. It will no. You can do it your hand. It will charge in just a few seconds. Give it some 1 minute or 30-40 seconds.
Yeah, just by the way, meanwhile checking if there are some Newton's method related questions that I could solve. Okay, I think we did cover that counter example, right? Whether it converges to a local minimum or not. So I think that's the example I want to discuss anyway. So
It, it, it just in my opinion, if we could get to do some programming assignments, this would be very clearly borne out these things.
programming assignments. Okay. I am not sure if I can do programming assignments because the set of topics and the rate at which he's covering for the last 2 weeks, I don't know.
Yeah.
The thing is,
If we
algorithms has taken somewhat of a backseat. So
Yes.
it's still, this is just the first week where we actually talked about algorithms, right? So even the
Yes.
template,
Yes.
broadly
Yes.
speaking, is not too clear at this point of time, right? Like what all
Yes.
things can
Yes.
be done. Uh,
Yes. Yes.
yeah, I don't know. I'm not sure. I can't promise anything at the
Yeah. If
moment,
you could.
but I'll try.
Yeah. If you could give some Python programs, maybe not too much complicated, then probably it will be a very good algorithmic perspective on the subject. I don't know.
Okay. Let me see. I'll try, but I can't promise.
Yeah. Okay. Okay.
Okay. So yeah, the other point that the second condition I was saying is, so you should be below this line, the one you see in green.
Okay.
But at the same time, you should not be below this line. So you should be
This
sandwiched.
line is a
Uh,
this line is the initial tangent, right? The second line.
no. Let me. So this line is basically C2 G naught, where C C1 C2 1. So this is our reference. This is the zero slope. Yeah,
Okay.
and this
Okay.
is my slope at the current point. The
Okay.
G dash 0.
Okay.
So I can look only with between this ring. No, it doesn't make sense to go below that.
Yes, yes, yes.
right? So thing
Yes.
is, I'm giving some upper. I'm first of all, I'm saying okay, don't go too far. That is dictated by this line.
Okay. C1.
Uh,
Okay. Okay.
yeah, and I'm saying, but also don't go too, but don't be too close also. So I'm saying okay, go at least a bit far. So by that, what I'm saying
Okay.
is this red line and this another blue line.
Yeah. Yeah.
So now my region will become okay. This is a very small region here because of my drawing, but it will be either this region or this region and so on. So here I think the way
Okay.
it's been drawn actually it perhaps gives a bad impression. Like it's not a properly drawn drawing. But I hope you get the point that I am only allowing to look in a certain region.
Yes. Yes.
So I am
Definitely.
saying you stay above this. I mean wherever this region corresponding regions are, and accordingly you stay below this red line in the corresponding regions. So the second condition corresponds to this, so that I don't stay, so that I don't end up taking two small steps. I end up going at least a bit farther.
Yeah. Means at the risk of this, we can stagnate, right? If we take two smaller steps, right?
Yeah, it will just become slow. Like, convergence would take a lot of time.
Yeah. Okay.
Right. I wanted to discuss something. No, I think we can. Yeah, we can stop here. I mean, I could maybe solve some more questions, but we are out of time. But in general, I would recommend that just keep this quadratic function in mind, and you can, um, depending on what the q the Hessian is, you could derive relations between gradient at a certain iteration with the gradient at the previous iteration or the first iteration and so on. So try out a few of these things. I will solve them to the extent that I can in the discussions. Otherwise, we can take it offline and discuss there.
Yeah. Yeah. Sure. Sure. Sure.
Okay, and yeah, so I was thinking of solving some problems like the one I had told you about, right? Where you look at the tangent cones and you verify the first order, second order conditions for directions corresponding to only those directions. So yeah,
Yeah. Two sessions back, right?
yeah. So let's see. I don't know if I first priority is to cover this material, and we can cover that in the rest of the time.
Yes. Yes. Sure. Sure. Sure.
Okay. So just let me stop the recording.